The stream started. Oh, so okay. Yes. So hello everyone. We will be starting from where we stopped yesterday. It's a study stream or whatever you can call it. We are exploring the what we are exploring. We are exploring this article or resource for scaling book, which is a scaling book for LLMs. So we studied that there are three. Wait, I have attached the I have attached the resources into the description. You can check it out. So yeah, there are basically three fundamental constraints. First is compute, then memory bandwidth, and third is communication between the racks or within the racks. So compute is how many floating point operation flops a chip can perform physically, and memory bandwidth is how fast data can travel from storage room into the processor's brain. So even if the process is too fast, basically even if the flops are compute is too fast, but if there is very less memory bandwidth, then there is a problem. And similar with the case with the communication. So basically, if the model is too large, too big for one chip, then you use thousands of chips to store your model. And there can be many reasons why you store, why you use more than one chip to store the model. So yeah, so communication between the chips is also equally important as compute and memory bandwidth for scaling the LLMs. Then we studied time to math that the computation flops upon the accelerator flops. So accelerator are nothing but uh, machines that like GPU, CPU we use to store models or accelerate the communication between them, something like that. Yeah. Yes, we were right there only. Communication between chips will distribute a model across multiple accelerators. Yeah, we studied the types of accelerator. There could be several types: ICI, DCN, PCIe. ICI is inter-chassis interconnect, which is a specialized ultra-high-speed network built custom by hardware manufacturers to link multiple AI chips together within the same server rack or adjacent racks, bypassing the CPU entirely. So, example for this is Google calls this ICI basically TPUs via optical circuit switches, or NVIDIA's NVLink. Example for ICI, inter-chassis interconnect. And then there is DCN, which is a traditional large-scale networking infrastructure that links thousands of independent server racks across the entire data floor. Yeah, and then PCI, Peripheral Component Interconnect Express. It's a specialized component physical infrastructure layer used to connect a computer's main processor, basically CPU, to internal peripherals like graphics card, SSDs, and other accelerators. And here we stopped yesterday, and now we will be continuing from there. We were in section 1, part 1, Introduction to roof lens. Okay, we were using, yeah, we were using Gemini and Gemini to read this article better, and Gemini also help us to create some notes. Which This is the notes which I have created, like uh, for the article thing. I have attached the link to this in the description, and also the resource link into the description. You guys can check it out. We'll be continuing in a minute. Just seeing that is my voice audible or not. Let me see. Yeah, I guess we are good to go. My voice is not very clear because I am using this Digitech mic and it's not very helpful. The voice is like echoing, something like that. But I guess it's okay. No one is watching. Well, this doesn't stop us. I think. Okay. By the way, today not yesterday on 9 June, Anthropic released their Claude Fable 5, which is a Mythos class model. And I have just, shoot a video, small video about what it does and few things about it. You can check it out in my channel if anyone is watching. Probably not, no one is watching, man. Okay, you can check it out and guys can show some support to me. So okay, now let's continue. So okay, communication between when we distribute a model across multiple accelerators, tensors frequently need to be transferred between them. There are often a few options for this on our hardware. Okay, yeah. If the communication is within or between chips, we measure this in bytes and estimate the total communication time within. TCOM is like total communication time, something like that. Uh, Typically, but not always, computation within a single chip can be overlapped with communication within. Yeah, yeah. So computation within a single chip can be overlapped with a communication within a chip and between chips. This means we can lower bound training and inference time by using maximum of communication time. We can also upper bound with the sum. In practice, we optimize against the maximum as the algebra is simpler and we can usually come close to this bound by overlapping our communication and computation. If we optimize with the maximum in mind, then the lower and the upper bounds differ by at most a factor of 2. Since T math plus T coms. What is this T coms? Literally. Okay. What is this T coms? Yeah, it's not. takes to complete a distributed computing step. Take it times time it takes for the chip processing brain to execute the material. Communication. The time spent moving data across the physical networks, like moving waves from engineering. The time spent moving data across the physical networks, like moving bits from HBM, high bandwidth memory storage into the core, or sending activation to another chip over ICI or DCI. Cool. Understood a little bit. It's not very easy to understand at first. I don't know. Okay, the entire goal of the high performance distributed AI engine is to arrange your architecture to T math greater than T comma. So compute bound. Basically, if the math takes longer than the communication, it means that chips can easily pass data to each other in the background while they are busy calculating. The communication latency is completely hidden. The hardware runs at the maximum efficiency. So where is my cursor? Cursor was fuck. That takes longer. Okay, okay. If communication takes longer than the math, your processing cores will finish the calculation instantly and then sits completely idle, freezing the system while waiting for massive tanks for data to travel across copper or optical lines. Whenever you see T-coms in the book, it is a reminder to calculate the exact time cost of the communication of the network transfer to ensure your data pipeline into bottlenecking your compute power. Okay, so it is saying that we can lower bound training and inference time by using the maximum of computation and communication time. So we can decrease the training and the inference time by utilizing the maximum of computation and communication time. So computation time is the number of uh, is the time to calculate flops or to do flops during point operations. The communication time is basically the time for the communication between the two hardware peripherals or hardware accelerators. So if you maximize the computation and communication time, basically if the computation time is more than the communication time, then it is good because while the computer or while the GPU is computing, the communication happening. But if the communication time is more than the computation time, then while the different hardware accelerators communicate to each other, the computation or the GPU is sitting idle, which is not good. So, okay, we can also upper bound with the sum. We can lower bound and upper bound. What does it mean exactly? Okay, What does it mean? Imagine you are running a restaurant to serve a dish. Check your internet. Bro, internet is fine, I suppose. Latency overlapping, also known as hiding communication behind communication. To understand what it means by the lower bound, best case scenario, the upper bound, worst case scenario. Oh, okay, so it is in the form of units. Okay. I'm too naive to understand these terms. I don't know. I'm not an engineer, but I'm a final year grad and I don't understand these terms. Fuck. I'm translating directly to the physics of an AI chip. Imagine you are a car manufacturing plant. The process has two steps. Sorry, a math unit worker physically assemble a car. Let's say this takes 10 hours. The comms unit, a shipping truck drives that finished car to the dealership. Let's say this ride takes 4 hours. He said. The LF system, the lower one. You're factory smart. You don't stop assembling cars while the truck is driving. When the truck is on its 4-hour drive delivering car, the workers are already on the floor assembling car. Because assembly 10 hours takes longer than driving. The shipping time is completely hidden inside the assembly time. The total time added to your timeline for that cycle is simply the maximum of 2. That is 10 hours. Okay. So it's basically the lower one is the best case. Okay, so lower bound is the best case scenario, which means the process time is more than the communication time. So the process is happening while the communication between the chips is also happening simultaneously. So that is the lower one. This is the case one. So the second upper one would be the communication time is more than the processing time. Basically, in this example, time to deliver the car, shipping the car is more than the time to assemble it. Now imagine a strict rule, secured the sequential system, the upper one. Now imagine a strict rule. Security protocols state the workers cannot touch a new car until the truck returns and confirms the previous car can deliver. Okay, now your customer, then everyone sits on the hand doing nothing while the truck drives for us. Then total time is 14 hours. This is your upper bound time. This is the worst case scenario where no overlapping happening and you are forced to pay the full price of both operations added together. This means in AI accelerator, inside an AI chip cluster, the hardware units are completely independent of one another. The metrics multiply units, mux, tensor cores, do the math. While the memory controllers, HBM, and the network ports, ICI and the link, handle the communication, they can run at the exact same time. The lower bound, well, the chip is a course of basic calculating the heavy math multiplication. Oh fuck. What is this? To sufficient HPC, exploring OLAP strategies using MPI non-blocking communication. What is this? Latency overlapping is nothing but ID communication. Lower bound means lower time. This formula is basically P. This is lower bound. We take the maximum of both. So that is the only time which is taken. Latency overlapping is happening over here. And here no latency overlapping is happening. Here the communication time and the mat time both is happening. So we optimize the maximum 9. I'm not sure what this. I understood this applications. Okay, I think I need to read it again. If we optimize with the maximum in mind, so if we optimize with the maximum in mind, okay, अगर हम लोग maximum को mind में रख के सोचे, then the lower and upper bounds differ by at most a factor of 2. अच्छा, ओके अगर हम लोग ने maximum को mind में रख के सोचा तो फिर lower और upper bound तो with an increased accuracy beyond this, the modeling overlap regions and overheads, which can be informed by profiling a specific model and target system. If we assume we can perfectly overlap communication and computation, when TMAC is written, we see full utilization from our hardware. We call this being compute bound. When TCOMs, we tend to be communication bound. And at least some fraction of our accelerator flops is wasted waiting for data to be passed around. One way to tell if an operation will be computer communication bound is to look at its arithmetic intensity or operational intensity definition. The arithmetic intensity of an algorithm is given by the ratio of total flops operations it performs to the number of bytes needs to communicate. Okay, number of operation performs to the number of bytes it needs to communicate either within a chip or between chips. So this gives the arithmetic intensity. So if we know the arithmetic intensity or the operational intensity, then we can say that we can actually tell that what case, I mean, which one of these case would be there. Like T math would be greater than T forms or T forms would be greater than T math. Or basically in simple terms, whether it would be computed by a bound or a communication bound. So if the arithmetic intensity is more, because if it is more, it means this is less. Hmm. So bytes, so if it is more, then it is compute bound, and if this is less, then this is communication bound. Okay. Arithmetic intensity measures the flops per byte of a given to a first order, where when our arithmetic intensity is high, the math is large compared to T forms, and we typically use most of available flops. When the opposite is true, we spend more time on counts and waste flops. The point where the crossover happens is the peak arithmetic intensity of our hardware. The ratio of the peak accelerator flops to the accelerator bandwidth. Crossover means what? The point where this crossover happens. Crossover happens basically the point where the communication and the compute is equal and they are basically increasing at the same time. Okay, something like that. Okay, the point where the crossover happens is the peak arithmetic intensity. So maximum would be one, I suppose, when these two are equals, or no, maximum would not be one. It would be maximum if this is lower than the peak arithmetic intensity. So when the communication flops per accelerator flops is more than the communication byte per bandwidth bytes. Okay, computation flops. So basically, all of this is saying only one thing, that if the computation, computation flops more, accelerator flop, whatever it is, its computation is more than the communication, then it is an compute intensive, or otherwise it is an accelerator intensive. Basically, it's something else, I suppose. The quantity engineer or whatever. Fuck, what is this? What is crossover and लगता सर्दी हो रही है भाई. Bro, who is this one guy who is watching me? Please comment down. Please. Want to know. This is guy. Anyways, okay. The screenshot or whatever it is. The symbol this means is logically equivalent to, yeah, fuck. The author is using this algebra. What is the goal set? What it means? We want our computation time, Tmath, to be greater than our communication time. Yes. As we can hide our network or memory latency in the background. Yes. The author replaces the abstract time variables with their real world physical definitions. Where the time for math is equivalent to total math operations you need to do flops. Total flops, okay? Time for math is nothing total flops. You do how many operations the chip can do per second. The total communication is total data you need to move or how many bytes to move per second. The second, the cross multiplication trick. Communication flops or communication bytes. It is total flops you have to do upon the total number of data you need to move, or how many math operation you can do per second, or how many data you can move per second. Okay. To isolate variables that belong together, the author does begin. Okay. Oh, crossover is the exact boundary line on the roofing graph where the chip operates at peak efficiency. Yes, that's what I meant. The chip operates at peak efficiency. Let's look at the number given in your text for the Google TPU V56. Okay, let's see how it looks. I mean, it's good to see visuals. Oh, did I copy it? Fuck. Google TPU V56 is a cost optimized tensor processing unit. TPU designed primarily for large scale inference and cost effectively of modules. Oh, fuck. I just dropped my mic. Mic drop moment. Silly jokes. And the cost effective training of models up to 2 trillion parameters. Announced it delivers up to 2.5 higher inference performance per dollar and 1.7 lower latency compared to the previous TPU full generation. Low latency means communication rate. 197 teraflops was the peak compute speed of the Google TPU V56 or the peak memory bandwidth. We calculate the hardware intensity crossover using formula from line 2. It is peak compute speed to the peak memory bandwidth. This formula. On this formula, how many operations, how fast the chip can move data per second, and how many math operation the chip can do per second, how fast the data can be processed, the compute can be happen this fast, and how fast can be the data can be transferred this fast per bytes. And that on yeah, right. Uh, how fast math operation the chip can do per second, and how fast the chip can move data per second. Chip can move this fast the data per second, 8.2, so it's 240 flops per byte. What is this 240 crossover number? Tells an engineer. Your layer code only performs 100 math operation. So it's basically saying that the communication per byte, the data gets transferred or the data gets reads, or the most more perfect word is this: the data move from chip per second. How fast the data chip can move data per second? How fast the chip can move data per second? Hmm. Okay, let's read it again. I understand it right. I think now it says that the math should be greater than communication. Basically, the compute should be greater than the communication between the flops of the data at the speed at which the data is moving from the chips. The compute should be happening greater than how fast the data is moving from the chip per second, and that is what it is. And then some cross multiplication, and if the intensity of the computation, I'm sorry, that's right. noise suppression है और क्या चाहिए सो कंप्रेसर कंप्रेसर क्या करता है साइड चेन डंकिंग whatever it is if I just so attack release or game ratio of what I don't know what compressor is. Okay, I will do the audio settings later. Um, mm, for now, read this. Mm, We can visualize the trade-off between memory and compute as another factor. You can visualize the trade-off between memory and compute.